So in this video, I'm going to go through some more probability calculations for normal distributions. So we're using the same population of people that have an average height of 170, so that's mu, and standard deviation of 10. So the first question is to find the cutoff for the tallest 20% of people. So let's draw ourselves a diagram for that. So x is going to be the heights of all our different people. And we know that the average is happening at 170. Let me just put in brackets here that standard deviation is equal to 10. So we're interested in the tallest 20% of people. So if I draw in my cutoff, so I guess here, and let's give it a name, I'll call it x for the cutoff. What we know is that this here represents the tallest people, and the area under the curve is going to be equivalent to the probability. So if we want 20% of people, that means the area in here has to be equal to 0.2. So what we should be able to do is go and look up in our tables what z value corresponds to this 0.2 area. Once we've got that, we should be able to use our equation to convert between a z-score and x, which is the actual height of someone. Okay, so first step, we need to figure out what 0.2 area is in terms of the z-score cutoff. So let me scroll over. So one way that we can do this is to use our normal distribution table that looks like this. So this is just the regular one. So this one gives us the z-score when we look at the area between the mean of 0 all the way up until that z-score we're interested in. Now we kind of have the flip side of that, in that our area is this back end, okay, which was 0.2. So if we want to kind of convert it over to what that table is showing us, we really need to look at what's happening between the mean here up until our cutoff point. So that's this part in here. So remember, if we convert that into a z-score, the mean goes to 0, and this is the value that we're interested in. So let's go and figure it out. The area in here is going to be 0.3, yeah, because the whole thing has an area of 1, so half of it is going to have an area of 0.5, and if the top bit here is 0.2, then that leaves 0.3 left over for this other bit. So let's go and look it up. So scanning through this, I think the numbers get smaller as you move to the left and smaller as you move up. So we're looking for the closest value to 0.3. I think this is pretty much as close as we're going to get. So that means that the z-score that corresponds is going to be 0.8, and the next decimal is 4, so 0.84. Now, an alternative way of doing this is to use the inverse tables. So for the inverse tables, you can just kind of directly use this 0.2 area. So let's go and look at that. So it's this one here. So it's telling you this is the area that I'm interested in, and I'm going to spit out the z-score corresponding to that. So in the case we just did, it was 0.2. If we look through it, should be able to find 0.2. It's here. So that's alpha, or the area in this bit. That means that the z-score is 0.8416. So hopefully you can see that using this other table, this is known as like the inverse table, you can get a little bit more accurate in terms of your result. And it's usually a little bit easier. So 0.8416. Let's just add our extra decimals on the end. So both of those methods I just showed you are kind of equivalent to each other. They get the same result. So now all we need to do is figure out, okay, if this is the z-score, what is that in terms of x, or actual heights? So we can go and rearrange this equation, which converts them. I want to rearrange it for x. So maybe I can just move this across. So rearranging for x, I'm going to multiply standard deviation up to the other side. And then I'm going to move the mu over to the other side as well. If it's negative here, it's going to be positive when it gets to the other side. So if I swap over the sides, we get that. So let's just substitute in. So z Ours is 0.8416 multiplied by mu, alright, which is 170. Sorry, multiplied by, this is the standard deviation, which is 10, plus mu, which is the 170. This works out to about 178.4, and since we are working in centimeters for all these heights, that's going to be the answer. So that means the cutoff for the tallest 20% of people is 178.4, i.e. another way of saying that is that we would expect 20% of people to be taller than this value. The next up, we're looking at the shortest 10% of people. So very similar process this time. Let's start with our diagram. So we know the mean is 170. This is all in terms of x. And this time, we're interested in the shortest 10%. So it's going to be on this side. I would expect my value of interest to be, because everyone's quite short in this group. And the area then needs to correspond to, so looking at 10% of people, it's going to be 0.1. If we want, we can pop in the equivalent when we go to the z scale. So we know this is 0, okay, for where the mean sits. And then this is what we need to figure out. So I'm going to leave this as little z. So again, there's the two different ways to do it using the two different tables. I'm just going to go ahead and use the inverse table again this time though, because it's much easier, I think. So what we're looking for is 0.1 in this end section. Remember that even though on the other diagram it's drawn as on the top half here, it's a symmetric curve. So, you know, less than this, I should probably put this in as negative x, by the way, since it's on the negative side. Oh, got that wrong. Negative z, I should say, since it's on the negative side of 0. This is still probably going to be a positive number, right? Because it's going to be a height. You can't really have a negative height. So anyway, let's go look up an area of 0.1. Alright, so 0.1 is our area. Doesn't matter that ours is drawn on the other side. I'll rub this one out. So looking for 0.1, I think it's going to correspond to this. So 1.2816. And again, I'm putting in the negative because it's on the left-hand side, so it's got to be smaller than 0 on our z scale. Alright, so now we should be able to go through and convert this over to an x value. So we've got our equation already rearranged here, so I'm just going to recycle it. So substituting in, the z value is this, 10 and 170. This works out to be 157.2. Again, the units are going to be centimeters. So what that's telling us is that 10% of people are expected to be less than 157.2 centimeters. So now we can do the last one, which is looking at the middle 50% of people. So again, let's start with drawing ourselves a diagram. So the middle 50%, so if this is the middle, I should probably write in the mean. So we're going to have some cutoff point here and some cutoff point here, so above and below the mean, where if we then work out the area in here, it should be equal to 0.5 for the 50% of people. So the cutoffs, I'm going to call this x1 and x2. And what we should find is if we convert this onto the z scale, this is 0 for the mean. This one's above the mean, so it should be a positive value. And this one's below the mean, so it should be a negative value when we do the conversion. And they should be kind of the same distance away because all of this is symmetric. That's an assumption of, or you know, a fundamental part of it being a normal distribution. Alright, so if we're going to use our inverse table, again what we're interested in is kind of the upper part area. So that's going to be like this part in here. Alternatively, you could use the bottom part as well. So if we have a total area of 1 under the curve, and this is 0.5, what I would expect is that this little bit in here from the middle up until our cutoff would be 0.25, which would leave this being 0.25. And if you did the same thing down here, alright, I'd expect this to have an area of 0.25. So we're just going to take one of them, because that's all we need for the inverse table, and we can go and look up what the Z value would correspond to here if we had 0.25 area. So going over here. So looking for 0.25, this one here. So the answer we get out is a Z score of 0.6745. Alright, and this one here, it should be the same distance since it was symmetric. So therefore it's just going to be, since it's on the negative side, the negative version for our Z score. So now all we need to do is go back and convert these into x1 and x2 values. And we've already got our rearranged version of the equation. So again, I will recycle it. So let's go for, I'll go for x1 first. So it's going to be equal to the Z score, 0.6745, times by sigma, which was 10, plus 170. In a calculator, this is 176.7 centimeters. So that's this point here. Sorry. Alright, and then x2 we can get the same way, subbing into this formula. The Z score this time is negative. And this one comes out to about 163.3 centimeters. Alright, which makes sense. It's smaller than 170. Alright, so that's the answer to this question. So the middle 50% of all observations occur between 163.3 centimeters and 176.7 centimeters tall. So that's all there is for this question, and I'll see you in another video.